So let's start. Hello everyone. I'm Kailash, PhD scholar from Nano DC Lab IIT Gandhinagar. Welcome to the live session 5 of the course Digital Circuit taught by Professor Santanu Chattopadhyay. We have this live session every Tuesday from 6 p.m. to 7 p.m. And the major goal of this session to understand some of the concepts which has been taught in the class via some of the questions, right? And this session will also help you to do your assignments and also will help you to prepare for other competitive exams. Let us start with the today's session. What we have done as of now in the digital circuit these sessions is that we've started in the week one about the introduction to number system, and then what we have done is we have studied the Boolean algebra. We have solved a couple of questions on the Boolean algebra. Then we have also solved questions on combinational circuit, logic gates. Last week we have done questions on multiplexer, decoders, and some of the arithmetic circuit. In this today's session, we'll be discussing about sequential circuit and some of the questions based on the sequential circuit. So let me start the session and with the very first question that we have two varieties of sequential circuits which we have. The first one is synchronous sequential circuit, and the second one is asynchronous sequential circuit. So, can anybody tell me what is the advantage of synchronous sequential circuit over the asynchronous is? Right. So, I have four options over here: low hardware requirement, better noise immunity, faster operation, or all of the above. Anyone? Please respond if you are here. You can type into the chat box the options. All of the above. Okay, so I have one answer that is all of the above. Apart from that, do you have any other answer to all of the above? Okay, so let me tell you the answer is the faster and the other options are actually incorrect because we have the sequential circuit. So the main benefit of the sequential circuit is it works on the clock, and because of that you can have faster operation, right? uh, Talking about the noise immunity and the low hardware requirement, so asynchronous circuit takes lesser hardware as compared to the synchronous circuit. So this you should know about the synchronous and the asynchronous one. It was a theoretical question. uh, let's move to some questions which is more numerical based, and please see this question and try to understand the question. So I will read out the question for you. Consider the D latch shown in the figure. So this is the D latch which I am talking about, and it is a transparent when the clock input CK is high. So if the CK is high, the data can be directly latched at the output, or it will behave as a transparent and has a zero propagation delay. So we are considering that it won't take any time to propagate data from D to Q. Okay, so there is no propagation time. So in the figure, the clock signal clock one, right? So the clock one is this, and this clock one has been provided to you see the D input of your D latch, and the question here is in the figure. The clock signal clock one has 50% duty cycle, so it has 50% duty cycle, right? And clock two, right, which is another signal, right? And it has been connected with the enable of the CK signal of your latch, and it has 1/5 of the period delayed version of clock one. It means if this is the T clock, right? So this is the T clock, okay? So the delay between clock 1 and clock 2 is 1 by 1/5 of T clock. If this is the T clock, this part, the delay is 1/5 of the T clock. So the question here is the duty cycle at the output latch, right? The output of the latch, this one, right? So in the percentage is, right? So what is the percentage or what is the duty cycle of this D latch will be? Uh, can anybody tell me what do you mean by duty cycle? Anybody knows what is the duty cycle?
On time upon total time.
Okay, so
Count plus.
this can be considered as T on versus T total, right? So that is correct, right? So that is my duty cycle. Now, can anybody tell me what should be the value or what should be the duty cycle uh, over here? Anyone? So,
Percent,
yes,
30%.
30%. So I have one option which says that it will be 30%. Any other answer? Anyone? So let us solve this problem and let's see if the answer is 30% or any other answer we will have. Okay, so you see here that this is the clock 1 and clock 2. What we will do, we will make the output. Okay, we will uh, take the output signal. Okay, so when clock 2 is 0, right? So we consider that initially our output was 0, so we can keep our output as 0, right? So it will be 0 when clock 2 is 1, right? So it is transparent, so clock 1 will be transferred, so output will go high, right? So you see this is one time, this is another, right? Similarly here it is, and here you have. Okay, so the clock 2, when the clock 2 will go high, and if the clock 1 is high, this will go high, right? And you see here the clock 1 has gone down, right? And the latch is transparent, so this output will go down here. Okay, and it will be down till till this part, right? So till your clock 2 becomes high, right? It will be down here, and then it will be up again, and the clock will be like this. Okay, it will be like this, right? Please note that the time here is the T clock, right? So this is the T clock, okay, and this part is 1 by 5 of T clock, okay. And so if this is 1 by 5 of T clock, so this part will also be 1 by 5 of T clock, right? So you agree with me on this particular aspect, right? So you see for how much time your this this thing is on. If you will observe this part, if you will see here, up to this is 0.5 of T clock, right? So this is 0.5 of T clock, right? And it is turned on 0.5 minus 1.1 by 5, so that is my 0.5 minus, so this is my 1 by 5, right? So this is 1 by 5, it means 0.2, right, of the T clock, right? So this will be 0.3 of the T clock. So if we convert this into percentage, so this will be 30 times of the T clock, right? So the thing here is that the output signal, this output signal is being turned on uh, only the time is 0.3 times of the T clock, 0.3 times of the T clock, right? So this is your on time. Off time is obviously this entire time will be the T clock, right? So if you see the duty cycle, what will happen is 0.3 T clock divided by T clock, right, into 100, right? So if you want into the percentage, and it will be 30%, right? So whoever has said that the 30% is the answer, that is actually correct, right? So did you guys understood?
Sir, sir, I have one doubt. Is it necessary to always give the answer of duty cycle in percentage?
Not necessary, not necessary. So in this question it has been asked like that, so you have to give the answer because it was actually one of the gate question, and in gate question, you know that answer is ranges from they try to make the answer in the integer form, right? And that is the reason why it is been asked like that. But it is not necessary to represent, because the duty cycle, the ideal definition of the duty cycle is the T on by T total, right? And this will be a value which will be between 0 to 1, right? And if you want to convert into percentage, multiply with the 100. That's how it is. Is that clear?
Yes, sir.
Any question, anyone? What I have done here, I have done nothing, right? What I have done is I have just made the output waveform, and I have measured, okay, what is the on time of the output waveform. We know the on time is 0.5 t clock. Then we also know that the this portion is 0.2 of t clock, because it is 1 by 5, right? And we have subtracted, right? So 0.5 minus 0.2 is 0.3 t clock, and if you divide 0.3 by the normal t clock, 1 t clock, and into 100, that will give you the 30, right? So the answer here is to fill is 30. Any questions as such? Okay, if you don't have any question, what I will do, I will go to the next question, and it's a very simple question where you have a NAND latch, okay, and the two inputs are P and Q, two outputs are X and Y, and in the circuit, it's a NAND gates have non-zero. So what it is been showing here, that this NAND gates, right, has some propagation delay. Let's consider this as TP, and this is TQ. And please note that they are saying that TP is not equal to 0, TQ is also not equal to 0. Uh, Also, TP is not equal to TQ. Okay, so this is another thing they are saying. So after that, what they are saying is the present input condition of the latch is P equal to Q equal to 0. So it is 0 here. Okay. If the input condition is changed simultaneously to P equal to Q equal to 1, if it is changed from 0 to 1 like this, right? So what will happen, and what are the output that is being expected over here, right? So I have four options. X and Y both are 1. The other thing is X and Y which both are 0. The second option is either X is 1, Y is 0, or X is 0, Y is 1, or either X, Y both are 1 or X, Y both are 0. So anybody want to answer this question?
Sir, second.
Second.
Either x equal to 1, y equal to 0, or x
Why?
equal to 0 or y equal to 1.
Okay. So why do you say it will be second? Do you want to explain? Hello.
Sir, because there is unequal propagation.
Yes.
So that's why. And, and the sir condition will change simultaneously. So I think the answer is B.
Okay. Let's see. Okay. Let's see what will be the answer. Anybody else want to give the answer? Anybody else? Okay. So if you don't have any answer, so let me try to solve the problem for you. Okay. So let me remove everything. Okay. So let me consider a situation that this is the faster gate. Okay. This is the faster one, and initially this is 0, right? If initially any one of the input of NAND gate is 0, what will be the output? Anybody want to tell me?
1.
1, right? Will be 1 and 1, right? Vimla, do you have any question? Yeah.
Nothing, sir.
Yeah. So it will be 1 and 1, right? So this node will be 1, and this node will also be 1, right? Because it is connected like that. And what you have done, you have made this node as from 1 to 0. Okay. Sorry, 0 to 1. And this also from 0 to 1, right? So what will happen if both the inputs of NAND gate is 1 and 1, right? The output goes to 0. Now the question is, which of the output will go to 0 first? Okay, because both of them will try to act simultaneously, and if this is the faster gate I am considering, it will become 0. As soon as it becomes 0, right, this node will become 0 over here, right? And if again any one of the input of the NAND gate is 0, it will remain in one condition, right? So it will happen that x equal to 0 and y is equal to 1 if your first gate is faster. Okay, if p gate is faster, right? If p gate is faster, x is equal to 0 and y equal to 1. Let me consider another scenario when the situation is different. Okay, in the situation is different, and the situation is like that. Uh, Again, 1 and 1 here, right? And this is the faster gate. Okay, and what happens? It both the nodes goes from 0 to 1, right? So what will happen is the input of this gate will switch first, so 1 and 1 will go to 0 over here, right? And this 0 will propagate over here, and the output will remain at 1, right? So here x is equal to 1 and y equal to 0 if the q gate is faster, right? Depending upon which of the gate is faster, x is either 0 or 1, or 1 or 0, right? X and y is equal to 0 or 1, or 1 or 0, right? So that is the reason why the second option is actually correct over here. Okay, so any doubts in the question number 3? Any doubts? No doubts?
No.
You didn't get it, Komal? Should I repeat, Komal? Okay, okay. So let me quickly repeat the question for you. Okay, the conceptually. This is a so this is a NAND latch. Okay, so if initially we are saying that both the inputs are 0. Okay, if both the inputs are 0 for any NAND gate, right? So if I write the truth table of NAND gate, a b y, right, 0 0 0 1 1 0 and 1 1. So the truth table of NAND gate looks like this. Okay, sorry, 1 1 1 0, right? So if any of the input is 0, if any of the input is 0, the output will remain 1, right? So we can directly write 1 over here, right? So if this is 1, this will be 1. Okay, now the thing is, consider any one of the gate is faster. So if this is faster, okay, and what I'm doing here is I'm changing this both the nodes from 1 to 0, sorry, 0 to 1, right? So both the gates will try to give the output. Which of the gate will give the first output will be the faster one, right? So this will for both the nodes of this gate has become 1 and 1. So you see the output will become 0, right? And if it becomes 0, right, it will come here, and this 0 1 makes the output, or the output will remain as 1, right? So x will be 0 and y will be 1, right? Similarly, if this is the faster gate, right, and the output goes from 0 to 1 both the end, right? This is 1 1, so this 1 1 will make the 1 to go to 0, right? 0 will come here, and this 0 or 1 will make the output 1 itself, so it will remain at 1, right? So the output will be either x equal to 1, then y equal to 0, right? So depending upon which of the gate is faster, either is equal to 1, y equal to 0, or x equal to 0 or y equal to 1, right? So that is the reason why the second option is correct. Here they have not said that, okay, which of the gate is faster, so we have to assume both the condition, right? And because of that, this is the answer. Any questions here?
Sir, I understand this, but I don't understand how will decide which gate is faster. Actually, I'm traveling.
Let me tell you, you cannot decide actually which gate will be faster. Okay, this is a one step above thing from the digital electronics. So, and this every student should understand. Okay, so let me simplify this for you, that which gate will be faster. That is not in our control, right? So when we design a gate and we fabricate a chip out of it, right, we make sure that both the gates should work at the same speed, right? So that is our goal. So if we want to design, so we make sure that this the propagation or delay of this gate is 10 picosecond, and this gate will also be 10 picosecond, right? But what happens during the fabrication, right? The properties of this gate changes, or it doesn't. It's not like whatever you intended to fabricate has been fabricated in the same manner, right? And everybody should understand all the gates are made using CMOS logic, right? So let me quickly make you the CMOS logic of this NAND gate. Okay, so this will look like this. So the NAND gate looks like this. If anybody knows, that is fine. If you don't know, let me tell you, right? So this is your NAND gate. Okay, this is Y, this is your VDD, this is your ground, right? And this will be your A, and this will be your B, right? It will look like this, right? So it is made up of transistors, right? And you understand that these transistors, which we have, uh, to have exact same transistor fabricated every where, it is not actually possible. Please note that this is not possible, and because of that, it may happen that this transistor is faster of one of the gates, and for other gate it is slower, and because of that, it happens that there is a discrepancy the delay of both the gates, right? So if you ask me that, okay, do I know a priori that which of the gate will be faster after fabrication, the answer is no, right? I cannot get a priori. As a designer, I don't want there should be any delay between both the gates, right? But because of the fabrication process which we have, the way we fabricate our chip, the final chip which comes, uh, the reason is that because of that, the nonlinearity in the fabrication process, we do not get exactly same the pinpoint up to decimal places. We don't get exactly same propagation delay because of the nonlinearity in both the gates, and that is the reason why we can have the same gates but with little bit propagation delay difference. And first we have to find out which of the gate is faster by doing by providing input, and then we can say that, okay, this is the gate faster, and this is how the circuit will work. Okay, and this will, if you will learn the micro fabrication, that is one of the courses that has been again offered by ISC Bangalore NPTEL course. You can go and learn this micro fabrication course, and in there you will actually see how each of these transistors are being fabricated, and why I am saying that there will be non-linearities in the fabrication, which will result into not having two identical gates despite being the design effort or making same identical gates. Okay, so that is my argument from my side. Hope you understood the concept, right? Why both the gates will not have the same propagation delay, and we cannot decide which of the gates will be fast. Okay, is that clear, or did I confuse too much?
Hello.
Yes.
Sir, if we change the input of P is to going to output Y, then my result is same output. Sorry,
Yeah. Can you repeat the question again? Yeah, I didn't hear.
sir. In the circuit shown,
Yes.
circuit which is shown, if
Yeah.
we change the connection,
Okay. Okay.
that input P input P to output Y and input Q to output X, and then my yes, yes,
This
sir.
is P, and this is
Then my
Q. You are
result
saying.
is same.
Okay, you're saying that it should be
In
like
in
this.
that in the, yes, sir. In that case, above NAND gate is faster or below NAND gate is faster.
Okay, so if you change the input connection, you're saying that will change the speed of the NAND gate? Is that what you're asking? If the you change the input connection?
Yes, sir. If we change the input connection, then my result, which is now you given, then this my result is same.
Yeah, it will remain same, right? Because both the inputs are identical actually of an NAND gate, right? So it doesn't matter you have connected over from this node or you have connected from this node.
Okay, then above NAND gate is faster.
It again, right? So the thing is, which one is faster, we don't know. So that's
So,
my point, right?
okay, sir, clear.
Huh. We don't know which gate is faster. It will be decided after fabrication, after you design a chip, right? Depending upon the nonlinearity and the process variation which comes due to the process, right? You will figure out that okay, which one is faster. Okay, so just consider this designing of these chips like you are designing say two flowers, right, in two different pages, and you will observe that despite how much you accurately design, right, the two flowers will look slightly different. Okay, and similarly this happens in the manufacturing of ICs also, see this kind of problem. Okay.
Okay, sir.
Moving to the fourth question, which is a very interesting one, and I want the answer from the students of this question. It's a 4-bit shift register, right? So everybody knows, right, what a shift register is, right? So whatever data you provide here in every clock, whatever data you provide into the data in, so this is your data in every clock cycle, the data will be shifted. Okay, data will keep on shifting, and the sequence of shifting, D in will first go to A, then A will go to B in the next clock cycle, B will go to C, and C will go to D, right? The question here is, suppose initial state is 1101. So this is your initial state. Okay, suppose if this is the initial state, what is the number of clock cycle it will be required to reach the state of 1111, right? So the question is clear, everybody, right? The question here says that if the initial state of this shift register, please note that it is connected by an XOR gate over here, right? And how many cycles it will take to make ABCD 1111? That's the question has been asked. Anybody wants to answer this question? I have four options: 1, 5, 10, and 4. Anyone? Anyone has the answer of this question?
Sir, 10.
10. Okay. Why do you say that? Have you calculated it, or how's it?
Sir, 4.
Hello? Uh, you're not audible if you're saying something. Okay, I have one answer which has been said as 10. What about the other students?
4.
4. Okay, so I have one answer as a 4. Okay. Uh, what about other students? Okay, so let me try this solution for you. So let us consider initially uh, this is 1101, right? So if my ABCD, right? If this is 1101, okay. So what I will do, I will make A plus B plus C plus D plus. Okay, so that's my next state. Okay, so please see here that this will be shifted, right? So if this will be shifted, what will happen? This will be 1 1 0. So that is clear, right? So this will be 1 1 0. Okay, Vimla is saying 10 as an answer. Okay, so let me uh, do this, right? So this will be 110, and what will be this one? Okay, what will be this one? uh, that we have to see, and this will be XOR of this one, right? And the XOR of the previous one, right? So when both the inputs are 1, right, so the output of the XOR gate is 0, right? So it will be 0, right? So next state is 0110. Okay, similarly, what you will do now, your present state will be 0110. Okay, and the next state will be let next state we have to find out. Okay, next state we have to find out. Okay, so if the my present state is 0110, right? So next state will be, so see, 0 will be here, right? 1 will be here. Okay, and then what will happen, these two nodes, this was 0. Okay, and the other node was again 0, right? When both the nodes are 0, so this will be 0. Okay, so this will be what we get is 0, so this will be 0 0 1 1, right? And similarly, if 0 0 1 1 will come here, right? So let me quickly do, right? So this will be 0 0 1, right? And this will be XOR of this one and this one, so 1 0, this will be again 1, right? So if 1 0 0 1 is here, right? So this will be 1 0 0, right? And this will be XOR of 1 1, that is 0, right? uh, then if 0 1 0 0 is here, right? So this will be 0 1 0, and the XOR of 0 and 0 is 0. Similarly, if 0 0 1 0 is here, okay, this will be 0 0 1 and XOR of 0 0, so that will be again 0, right? After that, it will be 0 0 0 1, so here it will be 0 0 0, and 0 XOR 1 is 1, right? And after that it will be 1 0 0 0, so right, so it will be uh, 1 0 0, right? And 0 XOR 1 is 1, right? Similarly, it will be 1 1 0 0, right? So the state will be 1 1 0, and 0 XOR 1 is 1, right? And after that it will be 1 1 1 0, right? It will be 1 1 1, and 0 XOR 1 is 1, right? So this is the state which I got, right? So what I have done is every time I shift this three number to next state, right? And I take XOR of these two. Okay, and let me count 1 2 3 4 5 6 7 8 9 and 10, right? So 10 is the correct answer. Anyone has any questions on this? Anyone has any question on this? How much cycle it will take? Yeah. Okay. So that was the fourth question, right? So where we have taken a shift register, 4-bit shift register to, uh, and the question was, if you have this pattern, what will the fine? How much cycle you will take to get to this pattern? Okay. So now moving to the fifth question, right? In the circuit shown below, the clock frequency. Okay. So this is the clocks, CLK. Okay. This is the clock. It is given as 12 kilohertz. So the frequency of Q2 is. So anybody wants to give me the answer quickly? It's a simple question. So you want to you please give me the frequency of Q2. Anyone? 6 kilohertz. Okay, I have one answer that says that it will be 6 kilohertz. Any other answer? Okay, so 4 kilohertz. Okay, Satyam has answered 4 kilohertz. So Satyam, can you unmute yourself and tell me why you say that it will be 4 kilohertz? Satyam? Okay, no. Okay, let me tell you what is the actual answer. Okay, so I have one table which I've made for this question, right? Let us see, right, how this work, and how we have generated this table. Okay, so we have clock cycle. Okay, so let me make this table for you. Okay, we have clock cycle. Let me write the present state just like what we have done in the previous table. Okay, then we will have the input what we have provided, and then you will have next state. Okay, next state. And in present state you will have q1, and then you will have q0. Similarly, in the input you will have d1, then you will have d2, right? And in the next state you will have q1 plus, and then you will have q2 plus. Okay, so if you see here, the q1, the d1 what you are getting, the d1 is q1 bar, right? So the q1 bar is coming here, and from here it is coming the q2 bar, right? So it is q1 bar and q2 bar. So this is your d1, right? And the d2 is q1 itself, right? So that's simple. Okay, so let us see the zeroth clock cycle. What will happen initially? Q1 q2 is 0 0, right? Consider q1 q2 as 0 0, right? uh, if the q1 and q2 is 0 0, so what will happen? The q1 bar and q2 bar will be 1 1, right? So q1 bar will be 1, q2 bar will be 1, and the d1 will be 1, right? So d1 will be 1, right? And because q1 is 0, d2 will be 0, right? So this is fine. Now what will be the next state? The next state is this one, from d1 will go to q1, right? So the q1 plus will be 1. Okay, and the q2, so this 0 will go to here, right? So this will be 0, right? So this is the next state. Now the next state will become the present state, uh, 1 0, right? After that what will happen? The 1 0. Let us see the d1 and d2, right? So d1 is q1 bar, q2 bar, right? So q1 is 1 and q2 is 0, so q1 bar will be 0, right? So if any of the input of an AND gate is 0, so the input will be 0, right? And what will happen to d2? So d2 is q1, d2 is q1, so d2 will be 1, right? Because q1 was 1. And now coming to the next state, uh, so the next state will be this 0, this 0 which is here will go here, so this will be 0. And this 1, right? This is in the d2, this will go here, right? So the input and the next state will remain the same. Okay, so it will go here, right? So now this 0 1 will become your next state. And when 0 1 becomes next state, let's see what is d1 and d2. So if 0 1 is your next state, sorry, present state, right? What is so if this is 0 1, so from here it is going 0. Sorry, from here it is going 1. From here, sorry, yeah, this is 0 1, right? So from here it is going 0. So this node will be 0. Okay, and this d2 is already 0, so this is 0 and 0, right? And what will happen? The next state will be 0 0, right? So we have started with 0 0, right? We came to 0 0, right? In how many clock cycle? 1 2 and 3, right? In 3 clock cycle, what we have done, we have come back to the initial state, right? So the q2 which we have, right, is actually changing uh, after every 3 clock cycle, right? So what will be the frequency of q2? This will be 12 kilohertz, right? Divided by 3, right? So it will be 4 kilohertz. So this is the final answer. So the answer will be 4 kilohertz. The frequency of Q2 is 4 kilohertz. Is that clear, everyone?
Yes, sir.
So, moving to one of the simplest question, that what is the minimum number of JK flip-flop required to construct a synchronous counter which counts 0 0, then 1 1, then 2 2, then 3 3, then again 0 0? Anybody wants to give me answer quickly? This is a very simple question.
2.
2, okay. There is one answer that says 2. Anybody else? Please note that you have to count 0, then 1, then 1. Okay, Ranjit Pandey is saying 3. Right? Anybody else? Okay, Satyam is also saying 3. Anybody else? So let's see if you want to have this, if you want to see this, right? So what will happen? The code for this 0 will be 0 0. Then for this 0, it will be 0 0, right? For this one, it will be 1 1. Sorry, 0 1. Then for, okay, Vimla is saying 2, right? Let's see. Uh, this will be 0 1, then 1 0 1 0, right? Then 1 1, then 1 1, right? So these are the 2 bits which will be representing the individual numbers. But what we have to do is we have to differentiate between this 0 and this 0, right? So these are two different states, and for differentiating, so suppose I am taking two variable like b and c for representing the 2 bits. I have to take another variable a, right, which will not be used in the state machine, but for differentiating this, what is actually required is so what is actually required is you put 0 here and 1 here, right? Similarly 0 1, right? 0 1, and then 0 and 1, right? You have to put this if you want to differentiate between these two states. Otherwise both the state looks same, right? So the very simple approach to find out the minimum number of flip-flops is you take all the number of states. So here we have 8 states, 8 different states, right? And you take log 2 of 8. Okay, so that will be log 2 of 2 to the power 3, and this will be 3, right? So the answer here will be 3. It won't be 2, because 2 state, if you would have counted 0 1 2 and 3, that would have been sufficient, right? Because only 2 state can represent. But here we are saying that okay, you have to represent 0 then again 0, and both the zeros are different, okay, not same. It is a 0, right, and this is 0 followed by 0, right? Then this one is coming after coming, so previous state was 0, but this one is, its previous state was 1, right? So you cannot have, you cannot tell that both the ones are same. Okay, so that's why you require 3, right? So if you have say 6 states, again you will require 3, right? So because whatever the number of state, you just have to take log of 2, right? And you just have to seal it. Okay, you just have to seal it, the greatest integer function, right? So for the 4 states, the out answer will be 2. For the 8 states, the answer will be 3. Anything between 5 to 8, the answer will still remain 3, right? Because you require minimum number of states. So this is the question 6. Any doubts? Any questions?
Sir, while designing synchronous counters, any counter, we just make the present state and next state, and the inputs according to the present state and next state.
Yes.
Then for what inputs we get one, we make a truth table, and depending on what inputs are one, we the input will be expressed according to the cues, right?
Yes.
So why should there be differentiation between first 0 and second 0? We just write the truth table and just find D what expression for D, right? Why should there be differentiation between 0 because 0 and 0 makes 0?
The expression for D you are saying? Okay. No, so what I am saying is when you write a state machine of this, right, or you want to write a truth table of this, right, you will have a present state, right? You will have a present state, and then you will have a next state, right? So do you think for this 0 and this 0, the present state and next state will remain the same?
I don't know. I didn't guess. I don't know.
The thing is, it will be different, right? Because for this, the present state and next state is 0, 0, but for this, the present state is 0, next state is 1. Right, and that is the reason why you need an additional step. Please note that that additional variable will not directly impact the output, but we require this 3 flip-flops if you want to design this. Okay.
Okay.
Yeah, so we have the last question. We will have 8 minutes. Okay, we will quickly do this last question. And yeah, I think you can answer this question quite easily now because we have done a lot of question. Please note that I have shown a binary counter. I already told you that it's a binary counter, and this is the clear button. Okay, and you have to tell me that which counter it is. Mode 2, 4, 5, 6. Anybody wants to give me the answer?
100, that is 4.
Okay, somebody saying that it is 4. Anybody else? Okay, mode 5. Satyam is saying it is mode 5. What about any other student? Anyone else? So let's see, right? So when this counter will be reset? That's the question. Okay, so this is a XNOR gate. Okay, this is an XNOR gate, and the clear bar button, right, is getting the output of the XNOR. So when the XNOR output will be 0 and 1. So when it is 0, 0, okay, 0, 1, 1, 0, 1, 1. So I'm just writing the truth table of XNOR gate A, B, Y, right? So this is 1, 0, 0, 1, right? So when both the inputs of XNOR are 0, 0, in that case, the output will be 1, right? And when the input is like 0, 1 or 1, 0, the output will be 0, right? So to clear, okay, Vimla is saying mode 4. So clear this, right? What you require some pattern which will give you 0, 1 or 1, 0. So 0, 1 or 1, 0 you want. So let's see. Right, so 0, 0, 0, 0. That is fine. That is my first state. Then 0, 0, 0, 1. That is also fine. Not resetted. Then 0, 0, 1, 0. We are also fine with that. Then 0, 0, 0. Sorry, 0, 0, 1, 1. We are fine. Then 1, 0, uh, 0, 0. Right. So when the input is 1, 0, right? So it will be reset, right? So after this, what will happen? The next output will be 0, 0, 0, 0, right? So when the input, because the cycle has already been completed, right? This cycle has already been completed. Before that, it cannot reset, right? After this cycle, the output will become 0 because you have achieved 1, 0 over here, or you have seen 1, 0 over here, right? It means how many patterns we are seeing here? 1, 2, 3, 4, and 5, right? And after fifth cycle, it will be resetted. So it won't be a mode 4 counter, rather it will be a mode 5 counter. Uh, does my argument seems valid to you guys?
Yes, sir.
So everybody clear on that?
So whenever it just it's a 1 0, immediately it resets, right? So even though we are considering that is also a state.
Yeah, you have to, right? Because this is a counter and 1 0 has already come, and after that it will be reset.
But it's done immediately. Obviously, we cannot see the 1 0 output in the output side, right? So the clear button is an immediate, even though it doesn't, it will not wait for the any clock circuit, right?
It's a
So
synchronous clear. Please note,
uh,
yeah, it's synchronous clear, so it won't immediately change the output. It will wait for the next clock to change the output.
could you please explain me regarding the synchronous and asynchronous clear?
Okay, so let me just give you an example of synchronous and asynchronous clear, right? And the thing is, so suppose this is my clock cycle, okay? If this is my clock cycle, right? And I have suppose the output is something which is remaining at which is suppose changing as like this, right? 1 0 1 0 like this. Output is also changing like this, right? And what happened if I provide a synchronous clear, okay? If I provide synchronous clear over here, right? So it is 0, and please note that here I am just considering the active high for simplicity, and I have provided synchronous this point, right? And I've kept it 1. uh, the if this is clock and if this is output of any circuit, right? This output won't go 0 immediately, okay? It won't go 0 immediately. It will wait for the next clock cycle. It will wait for the next clock cycle, and then only the output will go 0, right? So if I think this I have not taken a correct example over here. Let me tell you that, okay, if it is remaining 1 for this many cycle, something like this is the output, okay? As soon as you arrive at this clock, right, you see that synchronous clear is high, right? So the output will be like this, okay? Output will be like this. So that's how the synchronous clear works, right? It is synchronized with the clock signal. Now how an asynchronous clear will work, as soon as you get, so suppose instead of this synchronous, if this is asynchronous, right? So as soon as you get your clear signal, if this is your clear signal, if your output was like this, as soon as you get your clear signal, it will go down, right? It won't wait for the clock, right? So that is what we call as asynchronous clear output. Is that clear?
Yes, sir. Thank you.
And that is the reason why it is not mode 4, it is mode 5, because it is waiting for the next clock, because it will have some propagation delay, right? It will take time. The clock cycle has already gone, right? So that is the reason why it will be a mode 5 counter, right? So that's all for today's session, right? So I have taken some of these questions from a couple of websites. So these are whatever the question we are solving have been asked in GATE, EAC, and ISRO, BARC exams, right? So it will actually give you the idea how this kind of questions can be solved. So thank you everyone for joining today's session. Let's meet next Tuesday, 6 to 7 p.m.
Thank you, sir.
Sir,
Okay. Yes.
the clock and the gate has the different propagation delays. How will the circuit work?
If the clock and the gate has different propagation delay, how does the circuit work? The circuit will work, right? Why the circuit will have the problem, right?
Hmm.
So let me,
Can
I will explain. I will
no.
explain.
Will it be same for same mod 4 or like depending on the difference, it can be mod 4 or mod 5, anything?
No, no, no. If it has some delay, so again, right, the delay should not be greater than the time period. Okay, this delay should not be greater than the time period. Okay, time period of the clock. That's my consideration. So if this is my clock, right, and this output you got, so this is clear signal, right? And so see, as soon as the clock comes and you see that, okay, your the q1 q2 q3 has become 1 0, so 1 0 0 0, right? So suppose this has not 1 0, so 0 1 0 0, right? It has become like this, right? What will happen, because of this some propagation delay it will have, right? It will the reset will go, so initially it was 1, right? It will go low after some time, right? But because the binary counter has been considered that okay, it's a synchronous, it will see that is there any positive edge coming over here. There is no positive edge, so it will wait for the next positive edge to get the final output. The circuit will work perfectly. The only thing is the output is going, or all the q3, q2, q1, q0 is becoming 0 in this cycle itself or in the next cycle. That's how it you can see it is. Okay.
Okay. Okay.
Okay, then thank you everyone for joining. Let's meet next Tuesday, same time.
Good night, sir.
उधर